we are now here from Professor Yufei Zhao from MIT, who will talk about equiangularized and eigenvalue multiplicity. Okay, Professor, can you start?
Right. Yeah, thank you for the introduction. It's a pleasure to be invited to give this talk. So I'll talk about some work I've been doing over the past several years on a line of work related to equiangular lines and eigenvalue multiplicity. And this is, and you'll see, several works that are collaborations with many students and postdocs at MIT. To start off the scene, there are some very classical problems in mathematics having to do with optimal geometric arrangements. What's the best way to arrange balls or points on a sphere? And these are the problems that have captured the imaginations of, very famous scientists, including Kepler, Newton, and Gauss. So Kepler's names attached to the sphere packing problem. Kepler's conjecture says that the best way to pack spheres in 3 dimensions is how you see oranges are stacked in the grocery store. Right? And Newton actually, so Newton got into a famous debate with David Gregory, where they were wondering how many ways, what's the maximum number of balls you can put around the center ball if they're all unit balls. So this is known as the kissing number problem. And if you configure the balls like this, you get 12 balls, like the vertices of a regular icosahedron, but there's some space, and if you push the balls around, you can imagine possibly being able to insert a 13th ball. And Gregory thought that maybe that was possible. Okay, it turns out Newton was right, but it took a while to rigorously establish that you cannot put a 13th ball like this. Gauss proved a form of Kepler's conjecture, showing that if you restrict the lattices, then the best sphere packing is the one that you see here. So this picture, the second picture, is a picture denoting spherical codes, how to pack little balls around on a big sphere. So what's the best way to arrange points so that they're mutually far apart from each other? So these are just examples of very classical problems in mathematics having to do with optimal geometric arrangements. And there's been also modern breakthroughs, notably Tom Hales proved Kepler's conjecture, showing that the best packing in 3 dimensions is the one that you see here. Now, this was a tremendously difficult proof, partly because it also involved a massive computer calculation. And after this proof was first announced and even published, there, because you relied on the computer, not all parts of the proof could be rigorously checked. And then Hales spent the next decade and a half working on a formal proof that was eventually completed. And now there's really no doubt of this conjecture, the truth of this conjecture, but it really exemplifies in some ways the spirit of pure mathematics, where someone spends their entire career or a big part of it working on a problem that nobody doubted in the first place. But this was a tremendous achievement. And more recently, Maria Wiazowska proved the optimal sphere packing in 8 dimensions, and together with collaborators, also 24 dimensions. And for this achievement and other works, she received recently a Fields Medal. And so all of these are incredible results about packings and codes in small fixed dimensions. But our understanding in high dimensions is incredibly poor. So for any of these problems, sphere packing, spherical codes, if you ask what happens in n dimensions as n gets to infinity, or even 1,000 dimensions, our best lower bounds and upper bounds differ by an exponential factor in the dimension. Right? So our understanding of these problems in high dimensions is very, very poor, and there's still a lot of room for new understanding. So what I want to talk about in this talk is a different problem of also a similar flavor of geometric arrangements, for which we now have a pretty good understanding in high dimensions. And that is the problem of equiangular lines. Okay, so a different problem, but it's also about arrangements, and it will show us some interesting mathematics. And the question is, how many equiangular lines can you have in d dimensions? So I'm looking for lines all passing through the origin in d-dimension Euclidean space. such that they pairwise all form equal angles with each other. As an example, in 2 dimensions, you can have at most 3 lines, as shown here. If you try to fit 4 lines, you can't make them all equal angles with each other. Already in 3 dimensions, it's a little hard to imagine, but it turns out the answer is 6, as shown here, the 6 diagonals of a regular icosahedron. The exact answer is known in only finitely many dimensions, and there are some general bounds, and they grow quadratically in the dimension. Okay. And this is more or less the state of the art. So there are some very nice mathematics here. In particular, the upper bound proof is a very short and clever linear algebra proof that, if you study linear algebraic methods in combinatorics, you'll almost certainly see this proof. And this is more or less what we know about the general problem. There's been exciting recent work as well, but in the big picture, there's still this constant factor gap between the upper and lower bounds. I want to note that in all the lower bound constructions that give quadratically many lines, the pairwise angles all go to 90 degrees as the dimension goes to infinity. Right. So this is somewhat related to this fact in high dimensional geometry that there's a lot more room around 90 degrees than any other angle. If you pick 2 uniform random points on a high dimensional unit sphere, they're very likely to be close to 90 degrees. So there are a lot more room around 90 degrees. So it prompts the natural question then, what happens if you don't let the angle change? Right? So fix the angle. Fix an angle, how many equiangular lines then can you have with this given angle in d dimensions for large d? And we denote by n sub alpha of d the answer to this question. Now, what is the maximum number of lines in d-dimensional Euclidean space with pairwise angle, this theta, which is the arc cosine of alpha? In other words, you think of alpha being the pairwise inner product, and so that's kind of a fixed given parameter. And we're interested in what happens when alpha is fixed and d goes to infinity. So fixed angle, large dimension, how many lines can you have? It turns out that for a fixed angle, the number of lines grows linearly in the dimension, in contrast to the unrestricted angle case where the number of lines grows quadratically. And once you know that it grows linearly, the natural problem then is to determine the linear rate of growth. Right? What is the leading coefficient for this linear rate of growth? So let me go through quickly some history around this problem. Although equiangular lines have been studied for much longer, the first paper that gives a result on equiangular lines with a fixed angle was written in the 70s by Lemons and Seidel. And they showed that for the angle whose cosine is 1/3, they actually determined what is the maximum number of lines in every dimension. And in particular, for sufficiently high dimensions, as long as the dimensions at least 15, the answer is given precisely by this formula here, 2 times d minus 1. The next result came about a decade and a half later by Neumayer. And it shows that for the angle whose cosine is 1/5 for sufficiently large dimension, the answer is given by this exact formula, roughly 3d over 2. Neumayer also thought about the next case being following this pattern 1/7, and he couldn't solve it, and he actually notes in his paper that the next interesting case will require substantially stronger techniques, because he felt that there was a barrier to the next case, and this barrier was actually further clarified in subsequent works, and I will mention in a second. Progress on this problem stalled for quite some time, until more recently, a book showed that indeed for a fixed angle, the rate of growth is at most linear. Okay, so this was a claim I made on the previous slide. So this was rigorously shown by Book in 2016. And then this important work of Bala, Drexler, Kivash, and Sudakov showed that, well, okay, so we want to determine what is the actual optimal coefficient here. And you can ask, how does this coefficient depend on alpha? And you might suspect, based on everything I've told you, that this number might go up as alpha goes to 0, because for constructions with quadratically many lines, the angles approach 90 degrees, correspond to alpha going to 0. So it seems like alpha being closer to 0 is good for you. But somewhat counterintuitively, that is not the case. It turns out that this coefficient is maximized at alpha equals to 1/3, where this coefficient is 2. Right, so this coefficient can be at most 2, and it actually goes down for it's strictly less than 2 for other values of alpha. So this is somewhat counterintuitive, but there is no contradiction because we're still talking about a fixed alpha and d going to infinity. So Zilin Zhang and Sasha Polyansky then later determined this limit when alpha is bigger than some threshold. And this threshold comes from them solving a very interesting problem in spectral graph theory that I won't have time to get into. But the work actually clarified what Neumayer meant by the difficulty and the barrier he had faced in his 80s paper. This was the same barrier that these guys were stuck at. So our work then solved this problem completely. And so I want to use the rest of the talk to explain what is the solution and what are some of the insights that we learned from this solution. So this is a work with a wonderful team. So we were all at MIT at the time, although people have scattered to different places by now. So Zilin Zhang was a postdoc working with me at the time. He's now at Arizona State. Jonathan Tidor was a PhD student. He's now at Stanford. Yuan Yao was a PhD student. Was an undergrad, and Zhen Tongzhang was also an undergrad. And so they're both PhD students at MIT and Stanford now. So this was our paper, actually recently won a Fulkerson Prize that was announced earlier today. So this was a paper that we're very proud of, and that it solved this problem of equiangular lines. Okay, so it's a theorem, so I should tell you what is a theorem, although the actual formula may be not that important, but I should tell you anyway, so bear with me. So let me tell you exactly what the answer is. But more importantly, I want to explain how to think about the answer and what are some of the ideas that are involved. So the number of, so the notation we call n sub alpha of d is the maximum number of lines in d dimensions with pairwise angle arc cosine of alpha. Okay, so for some special values of alpha, namely when alpha is 1 over an odd integer, the answer has a simpler form. So this agrees with the examples that we saw earlier. So when alpha is 1 over 2k minus 1, the answer has this formula as long as d is large enough as a function of the angle. I should point out that here, this large enough actually hides something interesting. So in what we are able to prove, d needs to be at least double exponential in the parameters. And that is a limitation of our techniques. We don't believe that to be the truth. We think the truth is roughly polynomial in the parameters, but there's some limitations, and the limitations are also interesting. I'll get to that later in this talk. So this is just a special case. It's easy to present. More generally, if you give me any value of alpha, the answer has the following form. Again, I'll tell you what the answer is because it is a theorem, but maybe don't get too fixated on the actual formulation, because I think what is more interesting is to explain what are some of the ideas that are involved in how to think about this answer in the context of graph theory. So here is the answer. Pick alpha, so that is the given inner product, so some number between 0 and 1, and we'll make a transformation. It's lambda. So lambda is 1 minus alpha over 2 alpha. We define this quantity, the spectral radius order, k of lambda, and it's defined to be the minimum number of vertices in a graph whose top eigenvalue of adjacency matrix is exactly lambda. Okay, so how to think about this? So you're given this value lambda, and you look through all the graphs in the world, enumerated by their size. And for each one of them, you write down its adjacency matrix and check its eigenvalues and check its largest eigenvalue and ask yourself, is this number lambda? The first time you see lambda, you stop this process and record the number of vertices. Okay, so for example, when lambda is 2, so here are just some examples in the chart. When lambda is 2, coming from alpha is 1/5, through this transformation here. When lambda is 2, so we'll look through all the graphs and ask what is the smallest graph whose top eigenvalue of adjacency matrix is exactly 2, and it turns out to be this triangle and has 3 vertices, so k we set to be 3. Now, it turns out when lambda is an integer, k is always the next integer, but lambda could be some other algebraic integer, and then k could be more interesting, but in general, it's I don't have an efficient way to determine what k should be. You just have to search through all the graphs. Okay, so there are two possibilities. One is that there is some k, that there is some graph whose top eigenvalue is exactly lambda, in which case the answer to our theorem is that the number of lines with pairwise angle arc cosine of alpha for large dimensions is given by this formula over here, exactly for sufficiently large dimensions. Okay, so there's no error term here, but I do require the dimension to be sufficiently large. There's an alternate scenario where you give me some lambda, some alpha, and there's no graph whose top eigenvalue is exactly lambda. So for example, if you give me a lambda number that is not algebraic, then there's no graph. Right? So in this case, as a matter of convention, we set k to be infinite. And then the theorem is that the number of lines as d gets large grows like d plus a sublinear term in d. Okay, so we're not able to more precisely pin down what this should be. Well, we do have some slightly better bounds, but in general, this is little o of d. Okay, so that is the theorem, and that is the numerical answer that we're able to produce. And maybe I'll pause here and let you pause here for a second. But the rest of this talk, I want to explain what are some of the ingredients involved, and I think what are some of the interesting mathematics that are involved in the solution, and what are the open problems and future directions. A key result that plays a key role in our work is a new theorem in spectral graph theory on sublinear second eigenvalue multiplicity. So it says that every connected bounded degree graph has sublinear second eigenvalue multiplicity. And here we're always referring to the adjacency matrix of a graph. So more precisely, what we proved is that a connected n-vertex graph with maximum degree delta has second largest eigenvalue with multiplicity at most this bound, where the relevant thing for us is that for fixed delta, this quantity is sublinear in M. There's n over log n. Okay. So I think this is an interesting result on its own because it's a fairly general result about eigenvalues of graphs, and there are very few results about eigenvalue multiplicities of graphs. So spectral graph theory is often concerned with the spectral gap because of its relevance to mixing, to expansion, and that's very important. But not that much attention has been paid to eigenvalue multiplicities of graphs, and it's through the geometric problem that we encountered this result here, which played a very key role in our solution, but I think it's also independently interesting. To put in some further context, a very classical result of Perron-Frobenius from linear algebra implies that if you start with a connected graph, then its largest eigenvalue has multiplicity 1. So in a connected graph, or any non-negative matrix that's connected, the largest eigenvalue cannot have multiplicity. The largest eigenvalue is simple. So that's the Perron-Frobenius theorem. What our result is in the way of extension to the second largest eigenvalue, which can have multiplicity, but it turns out it cannot have linear multiplicity. Right? So the multiplicity of the second largest eigenvalue is always sublinear. So this is a very general result, which I think I hope is independently interesting, but also plays a key role in our solution to equiangular lines. So I talked about two problems that so far may seem disconnected but they're not. And so one problem is that of equiangular lines, another is that of eigenvalue multiplicities. And it turns out that these two are intimately connected, and this is a well-known connection that goes way back. In fact, in this classic graduate text in mathematics book by Gauss-Royo on algebraic graph theory, there's a whole chapter on the problem of equiangular lines, in which it calls it one of the founding problems of the subject. So I want to explain very quickly what this connection looks like in this context. Starting with a configuration of equiangular lines in RD, we can form a set of unit vectors by taking one vector in the direction of each line. There's a choice that you can make here because, instead of taking v1 like this, I could have taken the negative v1. But for now, I'll make that choice arbitrarily, and we can come back to it later on. Through this set of unit vectors, we can form a graph. Here's a graph where each vertex represents a vector. And between the two vectors, because we start with an equiangular lines configuration, the inner products can only be plus alpha or minus alpha. And so we can use edges to denote this combinatorial relationship. So we put an edge in if the pairwise inner product is minus alpha, if it's an obtuse angle, and put no edge if it's plus alpha or an acute angle. Okay. So this graph records the combinatorial data of this set of vectors. And it turns out that is the complete set of data that we require. Because given a list of vectors, v1 through vm, we can form its grand matrix. So this is a pairwise inner product matrix. It is positive semi-definite and has rank at most d because we start with vectors in d dimensions. This is a grand matrix, right? It's a pairwise inner products of these vectors. These are unit vectors, so has ones along the diagonal. And because of the equiangular nature, the off-diagonal entries are all plus minus alphas. Right? So it has a combinatorial structure, and this, which are plus alphas and which are minus alphas, is completely encoded by this graph here. So we can rewrite this matrix as in this form in terms of its the adjacency matrix of the graph. This is all the information that one needs, because from this grand matrix, we can do a Cholesky decomposition to refactor it into the original geometric information, the geometric data of the vectors up to a rigid transformation. Okay. So this graph is really all that you need to remember together with alpha and d. So the equivalent problem, the problem that is equivalent to the original equiangular lines problem, is to, given alpha and d, find the graph G with a maximum possible number of vertices n, such that this matrix here is positive semi-definite and rank at most d. Okay. So we reduce the problem to this, but also if you solve this problem, you can recover the original problem as well. And this graph formulation also gives us a convenient way to talk about constructions. For example, to verify that there exists a configuration of 12 vectors or 12 lines in 9 dimensions whose pairwise inner products are plus minus 1/5. Well, if I were to give you the vectors as coordinates, it would be quite unwieldy. They're complicated numbers. But a better way is to just show you this graph G. It turns out this is a graph. It consists of 4 disjoint triangles. And it's not too hard to check. If you have bit of time to think about it, it's not too hard to check that this satisfies the conditions that we talked about earlier, being positive semi-definite and rank 9. And this 1/5, it turns out to correspond to alpha equals to 2, has to do with the fact that these triangles have top eigenvalue 2. So that's the lower bound construction, and this is easily generalizable. But the more interesting part of the problem is to upper bound the number of vertices. So given alpha and d, we want to find a graph G with a maximum possible number of vertices n, such that this grand matrix is PSD and rank at most d. Okay, I want to upper bound this n. So this is an n by n matrix. So by the rank nullity theorem from basic linear algebra, we can write n as a sum of the rank and the nullity, which is the rank of the null space, a dimension of the null space of this matrix. The rank of this matrix is at most D because we started with vectors in D dimensions. And the nullity of this matrix, well, that's the matrix. It has this J, then O1's matrix, which is rank 1. I can take it out at the cost of adding 1 to the upper bound. And already you see that this nullity term is precisely the multiplicity of this lambda as an eigenvalue of the adjacency matrix. So already you see that eigenvalue multiplicity plays a role in the equiangular lines problem, right? So this is a link between the equiangular lines on one hand and eigenvalue multiplicities on the other hand. So the grand matrix is positive semi-definite, and because J is a rank 1 matrix, if lambda can be an eigenvalue of the adjacency matrix, it must be either the largest eigenvalue or the second largest eigenvalue. So, this being positive semi-definite really constrains what lambda can be. The largest eigenvalue case turns out to be the easy case, and that turns out to also be the equality case, corresponding to the configurations here where you have many disjoint copies of a single small graph. So the actual interesting problem is to rule out the possibility of lambda being the second largest eigenvalue. So you might naively ask, could it be that the graph cannot have large second eigenvalue multiplicity, in which case we will be done at this point? But that's not necessarily the case. There are some graphs, such as a complete graph, whose second largest eigenvalue is very large. Second eigenvalue multiplicity is very large. But it turns out that not all graphs can arise through equiangular lines. Now, remember at the very beginning of this setup, where we went from a configuration of equiangular lines to these unit vectors, we made a choice which direction this unit vector pointed. So we had to make a choice, but we could have made the other choice. Instead of V, we could have used minus V, right? And that changes the graph, right? So that changes the graph in a predictable way, namely it switches all the edges and non-edges around a vertex. A key step towards the solution is this following result of Bala, Drexler, Kivas, and Sudakov, says that for a given fixed angle alpha, there always exists some bound delta in terms of alpha, so that we can switch the graph so that the maximum degree is at most delta. So we only have to think about bounded degree graphs for the problem of equiangular lines, thanks to this important observation. So this is also a place where the graph theory framework plays an important role in the solution of the problem, because everything I've told you is just linear algebra, right? There's not really genuine graph theory, but the proof of this theorem here, at least the initial proof, used Ramsey's theorem, or used very graph theoretic ideas and techniques. Roughly speaking, the way it works is that you can observe that you cannot have a large clique in this graph, because a large clique would be a configuration of vectors, all with minus alpha inner products with each other, being very obtuse to each other. And there just isn't enough space to have a lot of vectors that are all very large angle to each other. So there's not a large clique. And then Ramsey's theorem tells us that not having a large clique implies there must be a large independent set. And then we can start with that as a starting point to get more information about the structure of the graph and to further refine the structure of the graph until we get that this graph can be switched into one that has bounded degree. So this is a part of the proof where graph theory is very convenient. And that brings us to this new result on eigenvalue multiplicity that I had mentioned earlier. So now that we're down to just bounded degree graphs, and it turns out that we can only, through other simpler arguments, we only have to worry about connected graphs. Combining everything that we've talked about with the theorem that we proved on the sublinear eigenvalue multiplicity of the second largest eigenvalue, we can then complete the proof, right? So because the second eigenvalue multiplicity is small, set into this bound over here, this shows that n has to be small in this case, which would then not be competitive compared to the actual equality case. Okay, so I want to spend then the next several slides discussing this result on sublinear second eigenvalue multiplicity. I think it's a really interesting result, and I want to just spend a bit more time explaining what the statement of this result is, and then I want to show you a glimpse of some of the key ideas in the proof, and also mention, what are some of the challenges to better understand this result, including bounds and upper bounds and lower bounds and variance. So all the adjectives in this theorem are necessary. If you can delete any word, then this theorem becomes incorrect. So for example, there's some near miss examples. So for example, if you take a complete graph, its eigenvalues are, well, if there are k vertices in a complete graph, its eigenvalues are k minus 1, the top eigenvalue, and then minus 1 the rest of the times. So the second largest eigenvalue repeats the rest of the way, right? So it has very large second eigenvalue multiplicity. It is also not a bounded degree graph. So that's, part of the reason why we need some bound on delta. The second example over here, well, here the spectrum of the eigenvalues of this graph are just you take one component, take its eigenvalue, and you repeat it many, many times. It also has a linear second eigenvalue multiplicity, but it is not connected. So the connectivity hypothesis cannot be removed. Here's an example where the eigenvalue 0 repeats a linear number of times. And here's an example of an eigenvector where all the unlabeled vertices are assigned 0 and these assigned 1 and minus 1. So you can check that this corresponds to a 0 eigenvector, but you can also move this leg anywhere else. That gives you linear multiplicity. But it is not the second largest eigenvalue. It's very far from the second largest. In fact, it's one of the middle, the center eigenvalue. In fact, I can modify this example somewhat to get the smallest eigenvalue, the least eigenvalue, to repeat linearly many times. So this is an example where the least eigenvalue repeats a linear number of times. So the theorem is really about one of the largest eigenvalues. It's not about the smallest eigenvalue, for which it is false. It's one of the largest eigenvalues. And if you change, lambda 2 to lambda 10, it's still okay. Right? So it's not necessarily the second largest, but it's about one of the top. Right? So if you ask for the 10th largest eigenvalue, it also has sublinear multiplicity, although some of the constants may change depending on what you change this number 2 to. But nevertheless, it's about one of the top eigenvalues. Okay. I want to explain a key idea that's used in this proof. So I won't show you the actual proof, although the proof itself is quite short. It only takes only about 2 pages in the paper. The paper itself is only 10 pages long, so it's a very short proof. And this eigenvalue multiplicity proof is not long, but I think it has a very nice idea that have not really seen it anywhere else. So we start with a more kind of commonly used observation that for a lot of problems related to spectrum, to eigenvalues, starting with a moment bound is often a good idea. So what a moment bound would tell us is that the trace of the power of this matrix is equal to this moment of the eigenvalues. And if we care about the eigenvalue multiplicity of this lambda, then we could just throw away all the terms that are not lambda, and this gets us an upper bound on the multiplicity. Now, this gives you something, right? This gives you some bound on multiplicity, but it's not a very good bound. You will not get a sublinear bound on it. So a key insight then is to first do something to the graph G so that we can strengthen this moment bound. And it turns out the thing to do that works is to first delete some vertices, in fact, a nicely chosen set of vertices. Okay, what does that do to this bound? So on one hand, deleting, let's say, a small number of vertices actually does not change the multiplicity adversely too much. And this is because of the Cauchy eigenvalue interlacing theorem. So the Cauchy eigenvalue interlacing theorem tells you that if you start with a matrix, right, with, let's say, n eigenvalues, an n by n matrix, and you delete the first row and first column, you get one fewer eigenvalues. Right? So, okay, we're only talking about symmetric real matrices. So we get, one fewer eigenvalue, and the eigenvalues interlace. Right? So they crisscross between the original eigenvalues. And if you have multiplicities, then the multiplicities then would also interlace. So if you have in the original graph a eigenvalue of multiplicity 10, and you delete one vertex, that multiplicity cannot go down to below 9. Right? It can drop by 1 at most, but it cannot drop by more than 1. Right, so that is very helpful. So if you don't delete too many vertices, then the eigenvalue multiplicity can be appropriately controlled. Another observation, and I'll just sketch a key point here, is that if you delete a net, meaning a set of vertices where every other vertex is somewhat close to one of your deleted vertices, then turns out the right-hand side has to go down significantly. Okay, so this can be proved using a fairly short combinatorial, closed walk argument, but it turns out to be extremely useful. If the right-hand side drops significantly and the left-hand side, the multiplicity doesn't get changed too much, then that turns out to be enough to do what we want. And by optimizing all the parameters, the bound that we were able to get is n over log n. And the natural question then is, how good is this bound? N over log n was the best that we could do. And, despite quite a bit of effort, we were not able to improve this bound in this generality. And it remains an open problem, how good is this bound? And I think it's very curious. And, I'm not sure. I mean, I don't have strong evidence to believe that this is anywhere close to the truth. And I'll say a little bit more about, what we know from lower bound side. But, earlier in the talk, for the application to equiangular lines, I mentioned somewhere that, for sufficiently large dimensions, we require double exponential in the parameters. And that corresponds to this bottleneck of n over log n. The best lower bound that we have, and this is joint work with 3 then undergraduates who have all gone on to grad school. So Milan Hyman, Carl Schreikerhold, and Shen-Tung Zhang. So we proved a lower bound that is roughly square root of n. Roughly speaking, so if you want to get a graph or a matrix in general to have eigenvalue multiplicity, it doesn't just come naturally, because if you start with a random matrix or something like that, then the eigenvalues tend to repel each other. So there's even the word eigenvalue repulsion that describes this phenomenon. So eigenvalues, they don't like to be close to each other. They certainly don't like to coincide. And if they do coincide to high multiplicity, often there is some underlying reason, right? So you need to kind of do something to really make them coincide. And one way to get them to coincide, one effective way, is to induce some symmetry in the graph. So for example, if your graph comes from a Cayley graph or has a lot of group symmetries, then any eigenvector you have on the graph could be used, you can use the group to spin the eigenvector to other eigenvectors. And that induces more eigenvectors and induces a high multiplicity. So that's one way to get high multiplicity. But this method of using group symmetry, it gets stuck at a certain point. Namely, it gets stuck at roughly root n, because the multiplicity that comes from group symmetries is the multiplicity, I mean, it comes from group representation. So the multiplicity is coming from the dimensions of the irreducible representations. And And that, cannot be more than root n, because, the sum of the squares of the dimensions of the irreducible representations add up to the order of the group. So whatever ideas that we had and used, we could push it to almost root n, but it could not go beyond root n. On the other hand, the best bound that we saw is n over log n. So there's a large gap, right? So there's a large gap between roughly square root n on one hand and nearly linear on the other hand. And we don't know which one the truth is closer to. So that is very much an open problem. In the same paper, we also constructed connected bounded degree graphs with many approximate second eigenvalues, meaning that if you don't care about having exactly lambda2 repeat, but having a lot of eigenvalues very close to lambda, then we can get quite a lot. And the interest in this statement here, so this is a different construction. And I think what is interesting about this construction is that the proof of upper bound, right? So this upper bound proof, it is an analytic proof. It's about inequalities. And it's a proof about inequalities, then you can you can insert some room for error. You can get the left-hand side to be not just about actual multiplicities, but approximate multiplicities. And the bound that we can get for n over log n also applies to approximate multiplicities. So for the problem of approximate multiplicities, this n over log n could be roughly tight. And that, I think, points to a certain limitation of our current methods. So we don't have a great way to distinguish approximate multiplicities, or certainly the resolution of approximateness versus exact multiplicities in the upper bounds. Okay, let me mention a few related results. Some of them have come after our work, but some of them we realized have been known earlier. So McKenzie, Rasmussen, and Shrivastava show that among regular graphs, they were able to improve our result from n over log n to n over polylog n. Okay? So there are some interesting ideas in there related to the typical cover of a random walk. There was an earlier work that we had learned after we wrote our paper due to Lee and Makarachov, but building on very classical, very important results from geometry on Gromov, Kodymyanakozy, and Kleiner. And in the graph theory world, it says that for non-expanding Cayley graphs, the second largest eigenvalue has bounded multiplicity. So in particular, if you take a Cayley graph for an abelian group or a nilpotent group, you're never going to get high second eigenvalue multiplicity. Interestingly, there's also some ideas that are carried back to Riemannian geometry from the work that we did. So here's a question that was asked, it's kind of a very classical question. What is the maximum multiplicity of the first non-trivial Laplacian eigenvalue on a genus G surface? So there is an upper bound that's linear in G. So this due to sort of a long line of works, and I think most recently, also I cited some of them on the slide here. And the best lower bound to this problem is on the order of root G. And there's a conjecture of Coulomb-de Verdier that this lower bound is asymptotically optimal. There was also an exact optimality conjecture that was recently disproved for a specific small value of G, but in any case, in general, this problem is quite wide open. Okay, so this gap between root G and G should look somewhat familiar if just by numerology. And very interestingly, a recent work of Cyril-Littré and Simon Machado, they showed that for negatively curved surfaces, so I'm going to be somewhat vague with exactly what the statement of the theorem is, but they showed that for a certain class of surfaces, they proved an upper bound of G over log G. And they actually took what we did, so what I've shown on in previous slides, this idea of net removal, and using that to induce a lowering of spectral radii. They used very critically these ideas and applied it to a Riemannian geometry context to prove their result about Laplacian eigenvalue multiplicities. Yeah. So I thought that was quite interesting, and so I'm hoping to see more connections like this from different areas of mathematics and transference of ideas. In the last part of the talk, let me mention some further problems and some directions that are related. So we've talked about equiangular lines, but more generally, we can talk about spherical codes. These are configurations of unit vectors in high-dimensional space. And you can constrain that their inner products all lie in some prescribed set L. And then ask, how many such unit vectors can you have in a given dimension whose pairwise inner products are constrained in some L? So the classical problem of kissing numbers or spherical codes corresponds to forbidding very small angles. And that corresponds to this L being this interval from -1 to some cosine of theta. So if you want all the vectors to be at least theta angle apart, then that's this problem of L codes. And the classical method that has been very effective in high dimensions for this class of problems is the linear programming bound pioneered by Delsart in the 70s. And a lot of the breakthroughs, especially in high dimensions, in fact, all the breakthroughs in high dimensions have come from the linear programming bound. But for low dimensions, other ideas, notably semi-definite programming bounds, have been also very influential in getting good bounds. The problem of equiangular lines is one where L is this set minus alpha and plus alpha. And as you saw in the talk, there was no linear programming bound. There was a very different attack, namely through spectral graph theory and eigenvalue multiplicities, introducing brand new ideas to this class of problems. There are many problems that are related, that are extensions of equiangular lines or variants of equiangular lines. And in general, we don't know how to solve them. Although we have some ideas, we have some partial progress. So for example, for spherical two distance sets where L is minus beta and plus alpha for two different numbers, alpha and beta, right? If alpha and beta were equal, that will be equiangular lines. But here there are two different numbers. There's some works that we initiated that solves the problem in some special cases and also proposes some general framework and general conjecture, but it is open in general. Another case that was more recent work with a couple of MIT students, so Saba Lapsveride and Alexander Sadashvili, where we looked at these types of codes L having this form. Okay, so let me not. Okay, so I'll see the next slide why this is interesting, why the specific form of L is somewhat special. But again, the story is that we can prove certain things, but the general problem is wide open. So we have some frameworks, we have some partial results, and a lot of open problems. And even for specific special cases, I think will be quite interesting. And for all of these, it seems to be a common theme is that we lack a useful generalization of the sublinear second eigenvalue multiplicity result. It will not be easy for me to say exactly what even a conjecture might look like, although I do have some ideas, but maybe more just how does one extend the ideas from second eigenvalue multiplicity to these other problems that are clearly very related, but for which we're just missing some important key insights. So let me just quickly mention why this linear code spherical codes problem is somewhat interesting. It's because Book showed that when L has this specific form, the rate of growth is also at most linear. Right? So here you allow a single positive inner product and a range of negative inner products. Turns out a single positive inner product plays a far bigger role than allowing the range of negative numbers. But nevertheless, the rate of growth is always at most linear. An open problem is to determine this rate. So this paper of Bala et al. Proved some bound that was a uniform bound for, that's an interesting bound. And we did, and the natural question then is for which values of alpha and beta is this upper bound tight? and we were able to resolve that question completely in our paper. But in general, if you ask what is the actual coefficient, we have no idea. We introduced some insights into the general structure of the problem, whereas so there's quite a bit on the slide, and I don't really want to spend too much time on it. But a big step in the equiangular lines problem says that the graph that we start with can be turned into a bounded degree graph. Right, and the bounded degreeness was very important. So what plays the role of bounded degree? Well, it's going to be something similar, but somewhat different. So we prove something that looks like a global structure theorem, which says that, if you start with a problem of this form and think about like what the geometry might look like and what the combinatorics might look like, it has a certain approximate block structure where after deleting some small number of vectors, there's at most some bounded number of parts. And other than on a bounded degree graph, all the inner products inside the parts are exactly alpha, up to bounded degree, number of exceptions. And also inner products between parts are, roughly the same number, some number, gamma that may differ from between pair of part to pair of part. So this looks like, if you've seen something like the graph regularity lemma, it has that flavor. But the key here is that there are some exceptions, right? So there are some edges in this graph that can differ from this template, and that difference actually is the key. So understanding, what is the bounded degree graph that lies on top is very much at the crux of the problem, and we don't particularly understand this problem, especially through the lens of second eigenvalue multiplicities. So we do formulate a conjecture that we call the modularity conjecture, which roughly speaking says that the optimal way to get a code is by adding these modular pieces on top of this template. Okay, so that's rather intentionally vague, but there are some actual statements in our paper that we were not able to resolve. So finally, there's a different topic that I didn't address at all, but I think it's very interesting that I should at least mention, is what happens for complex lines. So real lines, you know what they are. A complex line means that, well, in a line in D, okay, so in complex D dimensions. And there is a beautiful conjecture due to Zoner that in D-dimensional complex space, there exists D squared complex equiangular lines. Okay, a short proof is known that it can be at most D squared, but D squared is in fact conjectured to exist. So that's Zoner's conjecture. Okay, so just want to mention it. It's a beautiful conjecture. It's been verified in small dimensions, but open in general. What I've talked about in this talk, you can naturally ask the question of what happens for restricted angles. You fix an alpha, and then what happens in high dimensions? Almost nothing is known here, except a recent paper of Bala showing that the rate of growth is indeed at most linear, but the actual linear rate of growth is wide open. Okay. So let me conclude by just reminding you of the two main results. First, we determined the maximum number of equiangular lines with a fixed angle in high dimensions. And a key input to this result is this theorem saying that the second eigenvalue of a bounded degree connected graph is sublinear multiplicity. Thank you.
Thank you for your talk. Any question? Any question or comment? How to construct such equiangular lines explicitly?
Sorry, can you repeat the question?
Can I explicitly construct the equiangular lines in a fixed dimension?
Yes. So yeah, so you can take this grand matrix. So that's the matrix of inner products. And as long as this matrix is positive semi-definite, then you can do a Cholesky decomposition to recover the vectors that form this inner product matrix. Right? So that's the Cholesky decomposition, and that's how you can construct the vectors themselves. Now, they will have pretty nasty coordinates, and that's why it may not be the best idea to write down the coordinates, and it's better idea to write down their inner products, but nevertheless, you can use this to recover the actual vectors.
Okay.